In this video, we're going to be talking about extending carbon chain length. We'll go through several reactions which extend the carbon chain length, okay, and talk about what you can do with some of the products of that and go through mechanisms and equations as well. It's really important because this is how they complicate parts of your exam. If you ever come across a question where you have, for example, one less carbon in the reactants than you have in the products, then you've got to have used one of these reactions to extend the carbon chain length. So let's have a look at them. First one is formation of a nitrile. That's because you react a haloalkane with sodium cyanide or potassium cyanide in ethanol. And all of that is required. So you need the ethanol and you need to say whether it's sodium cyanide or potassium cyanide. Often though, we do the equations, we just show the cyanide ion and we don't show the sodium or the potassium because they are spectator ions. So we're doing that here with this chloroethane, adding to the cyanide, and then that goes to the nitrile compound plus the chloride, okay? It's actually called propane nitrile. Now, if we then go from here, you'll start to notice, hopefully, that the Cn minus is substituting with the Cl. And just to remind you, a nucleophile is able to donate a pair of electrons to make a dative covalent bond. Now, this is your nucleophile, so Cn. And the minus is not actually on the N, it's actually on the C. And we'll show you that when we do the mechanism. But this minus, okay, on this C is because of a lone pair of electrons which will donate to this carbon and substitute out the chlorine. Hence, this is nucleophilic substitution. So let's have a look at an example. 3-chloropentane plus sodium cyanide. We've included the sodium this time just in case you ever get that example. And you've got that making 3-cyanopentane, can also be called pentane nitrile, plus sodium chloride. Now if we draw this out, this is a good time, so if you're looking at the video, why don't you try and draw this out in structural formula, in skeletal formula to get that practice, and then I'll show you how to do it. So first of all, we've got chloropentane. So we do chloropentane, we do it with structural formula first. Okay, there you have your CH3 starting off. Okay, CH2, CH, and then Cl. Okay, so we've got to our 1, 2, 3. Okay, we're now going to go to our fourth. And there you have 3-chloropentane plus the sodium cyanide. Okay, and yes, we'll do, there's your sodium, and here's your cyano. Okay, and then we're going along 3-cyanopentane. So again, here we are, and this time we're going to put our Cn on there and then finish it off. Okay, and there you have your 3-cyanopentane. Hopefully you've drawn exactly the same thing. Okay, we just need to remember to do our sodium chloride. Okay, so our chlorine has been substituted with the Cn. So the Cn is now at position number 3. So this is at position number 3, and this is at position number 3. And we've substituted out, and this is nucleophilic substitution. Right, now is your chance to practice doing this using skeletal formula. So we're just going to do it with skeletal. So again, I'm going to draw 5 carbons. So there's 1, 2, 3, 4, 5. Okay, and then there is our Cl. So we've got 3-chloropentane plus the Na, and let's keep consistency here and do our Cn in blue. Okay, and then we do the skeletal formula again, 1, 2, 3, 4, 5. Okay, and there is our C. And notice it is bonding via the C. Okay, it doesn't matter whether you see it like in the previous slide with the minus afterwards. It's the C that has the minus. It's really important. And then plus our sodium chloride. Okay, and so here you have an example where you can do it in structural, you can do it skeletal. You've got to be able to do both, so it's well worth practicing. So again, I hope you got it right. Now let's move on to the mechanism. So we know our mechanism is nucleophilic substitution. And we know that our nucleophile is going to be this Cn-, but we know that the minus is on the carbon, it's not on the nitrogen. It's just the way you write it from left to right. Okay, and then we've got here our propane nitrile, essentially here. So let's now do the mechanism, but to remind ourselves, let's look at our exam tip again. So our exam tip is, for mechanisms, how do you do them? You draw your dipoles first. So let's have a look at our mechanism here. So I'm going to do it in skeletal formula. So there you have your Cl, and then you have your Cn. Now, remember I said the minus is on the carbon, it is not on the nitrogen. Okay, and that means there's a lone pair of electrons on that carbon. Now, if there's a lone pair of electrons on that carbon, we go for our next point, which is recognize the electrons, the lone pairs, the double bonds, and etc. So I know I've got, that's my recognizing the electrons. I know there's a lone pair of electrons on there. Okay, I haven't drawn my dipoles yet, so let's just get our dipoles on. So that is going to be delta positive, that is going to be delta negative because the chlorine is electronegative. Okay, our next point, draw a double-headed arrow from the electrons to the delta positive or positive charge. So here is my electrons, okay, double-headed arrow movement of 2 electrons going this time to the delta plus. So there you go, it's going to the delta plus. Our next point, count the bonds and remove any if there are too many. And you normally remove them by breaking the bond with the electronegative atom because electronegative atoms are good, what's known as leaving groups. They can leave quite easily and be stable enough to leave. So we have an electronegative atom here. Okay, so what we're going to do, to break a bond, we need to take the electrons that are in the bond, and there's a pair of electrons in that bond there, and we need to place them onto the atom. Okay, so therefore you get substitution. The C is bonded to the C. That means there's too many bonds to this carbon now because that counts as a bond. So this would be 2 hydrogens, two bonds here, and this extra one is 5, so too many bonds. Okay, so I take the lone pair 2 there, and by doing that I create too many bonds, so I have to get rid of one bond, which is this carbon to chlorine. I get rid of it by placing the electrons on. If that is the case, I then redraw. Okay, and I have my nice nitrile on there, and that is plus my Cl minus, and that's my lone pair of electrons that I placed on. And you can put it as 2 dots, or you can show, well look, that is that pair of electrons there. But either way, it's a lone pair of electrons. Okay, and that is how you do nucleophilic substitution to create a nitrile using a haloalkane and sodium cyanide in ethanol. We're now going to move on to another carbon chain lengthening example, still to produce a nitrile, but this time to produce a hydroxynitrile from aldehydes and from ketones. So HCN can be used via sodium cyanide and H+. Now there's a slight difference. If you're doing it from haloalkanes, remember it's with ethanol, but here you can just say sodium cyanide and put H+ aqueous next to it. Slight difference, which people often get wrong. And that will form a hydroxynitrile from an aldehyde. So, for example, propanal becoming 2-hydroxypropane nitrile with sodium cyanide and H+ aqueous. And we've still got this nucleophilic substitution again. So here's your example. It's that carbon that we're going to attack, okay, which is going to turn, using that sodium cyanide and H+ aqueous, into this hydroxynitrile. So a hydroxynitrile is when you've got a hydroxy and a nitrile or a cyano group here as well. Now let's have a look at this mechanism. Now this mechanism, unlike the other one, is nucleophilic addition. The other one was nucleophilic substitution. Okay, now we're going to react to the aldehyde with a Cn- nucleophile, remembering that the minus is actually on the carbon. Okay, and again, let's put our dipoles on like we've done before. Okay, let's find out where our electrons are. Well, there's our lone pair of electrons. Again, we've got the minus there, but remember, that's just the way you write it. I know it's confusing. Okay, and then you take your electrons to your delta plus carbon, but here is a really good point, is that you don't have to do it from the electrons, you can also do it from the minus. So in this example, we've done it from the minus going to the carbon. That means you've formed a bond, okay, from the carbon to this carbon, which means this now has 5 bonds. because it has 5 bonds, you need to get rid of one. Let's put one of those bonds on the electronegative atom, and there we are. Okay, that will then create this O minus. That O minus also has a lone pair of electrons, okay, and we can quench that with water. Now the reason we have water is because it is H plus aqueous, so there's lots of water around. That aqueous meaning there's lots of water. We can restart our mechanism order again. Remember that is draw the dipoles. So let's draw the dipoles, okay. And we can find out where our electrons are. Well, electrons are here, okay, and then we can take our electrons to our delta positive, and if there's too many bonds to the H, which there would be because this would be 1 and then 2, we need to break one of those bonds, and we normally put the electrons back on an electronegative element, which we do here, which then ends up in our hydroxy nitrile and OH minus remaining from the water. Our next example is hydroxy nitriles from ketones. Again, nucleophilic addition, okay, and again used via sodium cyanide and H plus aqueous. But this time, we're going to do a ketone. So this time propanone becoming 2-hydroxy 2-methyl propane nitrile. Don't worry too much about that name. Okay, but here we have our propanone. Okay, it's going to be on that carbon that we're going to add to. Okay, and it's going to create this hydroxy nitrile. This time we've got the nitrile in the center and not on the end. So, and again using sodium cyanide and H+. Now we know it's nucleophilic addition again, reacting aldehydes and ketones with that Cn- nucleophile. So if we look here, okay, there is our nucleophile again. Okay, here's our lone pair of electrons. Okay, first rule though, do the dipoles. Okay, so I've done that dipole, I've done that dipole. Okay, then I take the electrons from the nucleophile, or the minus, okay, and put it towards a delta minus. This time I'm doing it from the electrons. There's too many bonds to the carbon. There's now 5 bonds to the carbon. So therefore I break it and put the electrons on an electronegative atom, which is what I've done there, which then creates my O minus, okay? Now, the important thing here to show you is that this is done with H plus aqueous and sodium cyanide. So that H plus aqueous means you've got lots of water around, okay? But it also means you have H plus around. So if you don't want to do you want to do a less complicated mechanism, you can just quench it with H+, because that negative is going to be attracted to that positive, lone pair of electrons comes in, and you have your OH. And therefore you only have one product instead of that OH-, and it is a bit easier. Both are correct, so do whichever one you want, but do one of them. Our next reaction is the reduction of nitriles. Now that is where you add nickel catalyst and hydrogen, okay, to a nitrile to turn it into an amine. Notice with this one, there's no temperature required, whereas if it's hydrogenation, you need the same reactants, but you need 150 degrees Celsius. So this is a little bit simpler. So just nickel catalyst and hydrogen. We'll do it with our example here, which is ethane nitrile going to ethanamine, okay? And you need that nickel and hydrogen above the arrow. You don't have to write it within the equation, just above the arrow. And let's talk about 2 types of questions you're going to get from this. The first type of question is synthesis, where you just have multi-stage synthesis, and then this is one of the stages where you have to remember either the reactants or you have to get the reactants and then you work out what the product or the reactant is. But you can practice some of those in the synthesis video. Now, the other type of question, if we move this to the side and then look at our writing here, we've got balanced equations where you can often represent that reducing agent, which is H2, just as H square brackets. So if we're going to do H square brackets, we need to write out our equation again, which is CH3CN. And there is our ethane nitrile. That is going to go to our ethanamine. Okay. And then we have to think, how many H's do we add? To give this balanced equation, and remember they have to ask you to use H as the reducing agent in the question. Don't just do this, they'll ask you to do it. Okay, and then all you have to do is look at the hydrogens in the reactants, which in this case is 3, and then look at the hydrogens in the products, which is 3 here, so that's your original 3, and then I can see these 4 extra, 2 here and 2 here, so that's 4 extra. So to do the balanced equation, I just write plus 4 square brackets H. Okay, and that is how you do a balanced equation where they ask you to represent the reducing agent as H in the reduction of nitriles. Just remember that if there's more than one nitrile, you'll need double the amount of H's. So if there's 2 nitriles, 2 CNs, you would need 8 H's, 3 CNs, you would need 12, and so on. Okay, but it's as simple as count the difference between the H's and add what the difference is. Our last reaction of nitriles is just to look at how you hydrolyze nitriles. So it's really important that you remember this is a hydrolysis reaction because yet again this is another MCQ question where they can ask you to list which one or which one is not a hydrolysis reaction. And so really common one is this one in nitriles. So to do that, you just add aqueous acid, so H plus aqueous. Okay. So if we take a nitrile here, we've got ethane nitrile. The balanced equation is just to go from water plus a HCl in this case. We said H plus aqueous, but HCl is generally what's used. And then that will turn this nitrile into a carboxylic acid, plus this ammonium chloride at the end. Now, very, very seldom have I seen writing out this full equation, but what I've seen very often is for them to give you 2 products, again like a synthesis question, and then say, well, what is the reactant that turns this nitrile into a carboxylic acid? And it is H plus aqueous. You can also write that out as H plus / H2O. Now we're going to move on to electrophilic substitution. Remember, we're talking about carbon chain lengthening reactions. And if you've done this video in terms of electrophilic substitution before, you'll remember that you can add a carbon onto a benzene and form a carbon-carbon bond using aluminium chloride and a haloalkane. So if we go through this and we look at the different reactions again, just to remind you, generating the electrophile is adding that haloalkane to that aluminium chloride, and you get this CH3+, which is your electrophile, okay, plus this AlCl4, which we'll use later on to turn back into AlCl3 and regenerate the catalyst. Okay, it is an unfamiliar mechanism, but it's one that you should know. Okay, you take your electrophile here and you follow our rules and you say, where are the electrons? Where's the dipoles? There's no dipoles whatsoever. There is a positive charge here. Okay, so that means it's an electrophile because it's got that positive charge. It can accept a pair of electrons. So in the benzene cases, the pair of electrons comes from the benzene. And then that therefore is electrophilic substitution, and I'll show you why it's substitution next, because the hydrogen is leaving. So if you remember this from before, this is a smiley face right here, and it misses off 2 of the sections because if you think there's 6 electrons in this delocalized ring, okay, so I've removed 2 of them, I've removed 2 parts of the 6 sections because there's 6 electrons in the delocalized ring. Okay. Then from that point, we've got to get our product, we've got to cancel that out. There's too many bonds to this carbon if we put the ring back in, because if we put the ring back in, we must only have one hydrogen, or CH3 in this case, coming off each carbon. So we take the electrons from there and we put it back in, and that will restore this delocalized ring. And there you have your methyl benzene product, and you've formed your carbon-carbon bond. You've substituted out that H+. Now all we have to do is create the catalyst. So you start off with AlCl3. It turns into AlCl4. The AlCl4 adds to your H+ that you created in the mechanism, and you get HCl and your AlCl3 back, which means you're regenerating your catalyst. Now hopefully that should just be a reminder. We're now going to go on to do the second one where you form a carbon-carbon bond, which is Friedel-Crafts acylation. So Friedel-Crafts acylation is done using a acyl chloride and with aluminium chloride again. And again, you're forming this carbon-carbon bond, which is why it's in this video. If we go through the different reactions again, the different equations again, you can see exactly the same on using the AlCl3 with the acyl chloride. The chlorine leaves, turns this into AlCl4-, and you get this electrophile. The electrophile then does the same thing as we've done before. It's going to accept a lone pair of electrons from the ring. And then you're going to get this intermediate with this smiley face. Okay. And therefore, to restore this delocalized ring, you need to put 2 electrons back in because you've taken 2 electrons out. They come from here and they go back in. And then you get your product. And that's, if you see a benzene with a carbonyl right next to it like that, then you know it's from Friedel-Crafts acylation. Now, last thing again, we've got the H+ that's been substituted. Okay, and we take the AlCl3, which has been turned into AlCl4-, add the H+ to it, and you get your AlCl3 back again. And hence you're regenerating the catalyst. And I would just recommend that you do this regularly. Just go over your mechanisms, make sure you've really drilled them in before you do your exam.